Multivariable calculus, we're on 13.3, day 1, and you can see our learning targets at the top of the screen. I can find the lengths of parametric curves. I can find curvature of a vector function. So going back to your days in BC calculus, this is something that you hopefully have seen before. I know you have seen before. The arc length for a parametric function. Well, it's going to be integrating with respect to t, integrating from a to b. Inside the square root, you have dx dt squared plus dy dt squared. In 3 dimensions, you could have a very similar approach, and this is going to hold true for a vector function, where our I component is having f of t, g of t for j, and h of t for k. You can see now we're going to have just this z component, this extra dimension thrown in dh dt squared. It looks incredibly similar, but realize we've just taken derivatives of vector functions just previously. R prime was f prime of for our x component, g prime for our y component, and h prime for our z component. That's for multiplied to unit vectors I, j, and k respectively. But if we wanted to find the length of that derivative vector there, the length would be the square root of f prime squared plus g prime squared plus h prime squared, which all of a sudden you'd say, now wait just a moment, isn't that what we just have? That's definitely true. What are we seeing? This is fantastic. What you can do is more or less say the arc length on a curve defined by a vector function. We can integrate from a to b and just have the magnitude, the length of r prime of t in our integrand. So, wow, let's go ahead and find the length of a helix defined right here, going from 1, 0, 0 to 1, 0, 2 pi. And please do understand, I think what can immediately jump out and confuse kids sometimes is they can say, wait a minute, is this not an x, a y, and a z? And indeed they are. And then, kids can think, well, wait a minute, if these are our x, y, and z components, what in the world is going on then for our t values? Because as you're looking at your integral, you can see that we have a dt in there. Our bounds of our integral are going to be t bounds. So something that you want to train yourself very early to look at is that they will give you a t value generally, or something that you can solve for t. And you can see very quickly that t is going in this z component from 0 to 2 pi. That tells you something wonderful, that this t value, it's going to be starting off at 0 and going up to 2 pi. This is going to be our boundaries on our integral. That's so critical. But look, if we took r prime of t, and tell you what, for the sake of speed here, I'm just going to write this in component form. Derivative of cosine, we get negative sine. Derivative of sine, we get cosine. And the derivative of t, we just get a 1. And then if we were to find the length of this, the magnitude of it, by the way, on the TI-89, it's also called the norm. And as we just found this all out right in here, well, you're going to know that sine squared plus cosine squared is itself 1. This right here is a 1, and 1 plus 1, that's going to be a 2. So we're going to get radical 2. So L is going to be the integral from, well, what's our first t value? Well, it's 0. What's our ending t value? Well, we just saw right here, it's 2 pi. And inside, what's this r prime of t's magnitude? Well, that's just radical 2. And right now we can very quickly just do the fundamental theorem, and it's not going to take you too long. Plug in your 2 pi, you'd get a 2 pi radical 2 minus a 0. You can see that your arc length can be found very quickly. And we will just be left with a 2 pi radical 2. Okay, so at this point then, the arc length function. The arc length function, well, you can see, what if you just wanted to say, I only want to go to a certain t value? Well, we can write an accumulation function. We can write an accumulation function. And by the way, here's some review from our days in calc. We can say, hey, you might remember we had accumulation functions. We could say g of x could start at some value at a and go up to x, and then we could have f of u du. And we could say, look, we're going to integrate up to a particular x value. And you know, that's kind of what we did. Why am I bringing this up, though? Very naturally, we then took a derivative. You might remember what we did. It was, you know, nice and short. We just plugged that x right in, and we saw that that would just be f of x. Why is that so important? When we take the derivative of s of t, you just plug that t in there, and we get r prime of t. This is such a critical step right here. We're going to need this in just a moment, as we will really work out and derive a curvature definition, and we're going to need this step right here. But ds dt, taking the derivative of the arc length function with respect to t, it's just the magnitude of r prime of t. So let's take a look right here at page 2, and it says reparameterize the curve. Which, by the way, if you look at that, that's what we did for example 1. This is example 1's problem, so we're going to come right back to it, and hopefully that's going to speed some stuff up here. And it says, with respect to arc length, well, from example 1, we saw just a moment ago that the length of r prime of t is actually radical 2. And where did we do that? Well, we did it right here. And, you know, now we want to reparameterize. So write this curve out, but not with respect to t, but with respect to arc length, with respect to s, in the direction of increasing t. So, wow, right now you can think, my word, what in the world can we do here? Well, let's just remember this definition right here. I'm going to recopy it. We could say s was equal to this accumulation function. We could say 0 to t. We'll have r prime of u du. And my word, right now we could say, well, wait a minute, this is really just going to be a radical 2 here. And if we went ahead and if we did the fundamental theorem right here, we'd have radical 2 u, and then when we plug in a t, when we plug in our 0, that wipes out. So what are we seeing? S is really radical 2 times t. That is the critical step. You see, when they're saying reparameterize, they're saying, look, it's fine to have your vector function with t's in here, but we don't want to have t's in there anymore. We now want to have arc length. We want to have s in there instead. And tell you what, this is really what's happening. We're going to solve for t, and we'll get t is equal to the arc length divided by radical 2. And once we have that, guys, all you have to do is substitute that in. So I'm going to write this off to the side here. I'm going to say, here's r, but I'm going to say that t is really a function of the arc length here. So we can write this out in ijk form here. It's the cosine of t, but instead of having the t there, remember what we've got is t is s over radical 2. So I'm not going to write the t in there. I'm going to write that as s all over radical 2, and that's your I. And I just want to show you, you will have to write out ijk's sometimes. You'll have sine, and for your t again, it's s over radical 2 here. That's your j times vector j. Finally, we've got our t here. Well, that's s all over radical 2, and that's times a vector k. So this is reparametrized. Your vector function now has arc length in it. And in case someone said, well, when the arc length measured from a certain point is a certain value. And by the way, I did want to point something out right here. This is so critical. This is t. Remember, z was equal to t. This is your start right here at the 0. The fact that that's a 0 down there is very important. That obviously could change, if we would have had something a little bit different. All right, well, as we're continuing, recall that the unit tangent vector is r prime of t, but we divide by its length to guarantee that we have a length of 1. Well, let's just consider unit tangent vectors at equally spaced points on a curve. You can see this is the picture right here. So all these little arrows, all these tangent vectors have a length of 1, but they're at equally spaced points on the curve. In other words, our arc length is always going to have uniform spacing right here. And you can see what can happen. Your unit tangent vectors obviously can be pointing in very different directions, indicating the direction of motion at a particular point. And you can see that's going to change. So as we're thinking about this, you can think, well, perhaps that would be a great way to talk about the way the curve is changing. In fact, the curvature. So curvature is really a rate of change. Curvature is a measure of how the unit tangent vector is changing with respect to arc length. Obviously, the length of a unit tangent vector isn't changing, but its direction is, most certainly. And this is a way to measure that rate of change. So kappa, by definition, is going to be the length of the rate of change of the tangent vector with respect to arc length. Well, you can think, how in the world can we get a nice formula? Because generally we don't see equations for vector functions written out with respect to arc length. And you can think, is there perhaps another friendly way to write this out? Yeah, let's just remember Leibniz notation for the chain rule. If we were to take the derivative of a tangent vector with respect to t, we could go ahead and say, through Leibniz notation, you've seen this before, it would be dt ds times ds dt. It's like saying, taking the derivative of the inside portion. And really what we're trying to do is, we're trying to solve for this thing, right? We're trying to get that alone. So what we'll do is we'll do that. Let's get this by itself. You could say we'll divide both sides by ds dt. So, I do this, I do this, these wipe out, and you can see where we're going. But recall from page 1, remember I made a big to-do about that. ds dt is really the length of r prime of t. So we're going to say down here,